this problem we have 1.84 gram of a mixture of calcium carbonate and magnesium carbonate are heated strongly till there is no further loss of weight take place. The residue weighs 0.96 gram. Then it is asked to find the percentage composition of the mixture. That is, you may be asked to find the weight percentage of each component in the mixture. Look at the solution, dear students. You have calcium carbonate, which is a solid indeed. You know that the carbonate of the 2A group are unstable to heat. So when they are subjected to heating, the oxides along with the CO2 gas is obtained. You know that this MgCO3, I mean magnesium carbonate and calcium carbonate, when are heated, are totally converting into their oxides. Now in such case, we have to assume the weight of each component in this particular question as X, and the weight of this will be 1.84 minus X gram, because given the total weight of these two as 1.84 gram. Hence, after finding out the initial weights, you have to convert this into the gram moles by dividing with the molecular weights. You know that the molecular weight of CaCO3 is 100 and molecular weight of magnesium carbonate is 84. 24 plus 60. Now after getting this, you can see the information is regarding the weight of the residue. Hence I will be converting this entire data into the weight of residue. You can see here that residue is a mixture of CaO and MgO. Residue is something that will remain in the vessel after the reaction. You can see here carbon dioxide elopes from the vessel and only CaO and MgO remains. So what I am going to do, I am going to convert the entire data into that. As you can see, this is a balanced equation where the mole ratio of the reactant and product is found to be 1:1. Hence the number of moles of CaO obtained are equal to that of CaCO3, and number of moles of MgO obtained from magnesium carbonate are equal as well. Now you got the number of moles of CaO, which is equal to weight by molecular weight. Here also number of moles of MgO, which is equal to weight of MgO divided by molecular weight. Hence, when you sum the weights of the calcium oxide and magnesium oxide, it's given in the problem as 0.96 gram. You can see from the above information, we have got the weights of CaO as well as MgO in terms of X. I mean to say weight of CaO here, cross multiplication will give you 56 X by 100 plus weight of MgO is 40 by 84 into 1.84 minus X, which is equal to 0.96. So what I mean to say, that you have this equation which has only one unknown, X is nothing but the weight of CaCO3. So what I will do finally is that I will solve this equation for the value of X, and after solving I will find out the percentage composition, that is weight percentage of CaCO3, which is equal to X, weight of CaCO3 divided by total weight into 100. So when I am substituting the value of this thing, I am getting this as 54.55 percentage. So the percentage of magnesium carbonate will be 100 minus of this, which is turning out to be 45.65. So here we got the answers. First we obtained the values of X, and from there we are getting ultimate answers as 54.35 and 45.65 percentage of each in the sample. In the next problem, we have 1 gram mixture of potassium chloride and potassium iodide precipitated with silver nitrate giving 1.618 grams of silver halides. Calculate the percentage of each in the mixture. In this problem, we have potassium chloride. Its aqueous solution is being treated with silver nitrate to give you AgCl, is a white precipitate, and potassium nitrate. Likewise, you have a solution of potassium iodide which is being treated with silver nitrate again to give you this time silver iodide and potassium nitrate. So you have to write the concerned reaction and then you have to see whether all the elements on both the sides are matching or not. I mean to say whether this equation is balanced or not. After that, after knowing that yes, it is balanced on all the cases, move ahead by taking the total weight of the mixture, which is given as 1.0 grams, and in that the total mixture is 1.0. I'll assume the weight of KCl to be x gram, and this is 1 minus x gram. I know that when I am going to divide the weight with the molecular weight, I am going to get the number of moles. 39 plus 35.5, 74.5 are the number of moles of KCl which are being taken in this mixture, divided by 39 plus 127, that is 166 molecular weight, will give you the number of moles of Ki. Now you just notice that 1:1 is the mole ratio of these two substances. I mean to say, for every 1 mole of KCl, you are getting 1 mole of AgCl. If I take this many moles of KCl, I will be getting the same. These are the number of moles of AgCl which are obtained. Likewise, you see here, this is also lying in 1:1 mole ratio. When I get the number of moles of Ki, quickly I will be converting that into the number of moles of AgI, since the number of moles of these two are equal as they are reacting in 1:1 mole ratio. Now I will write the number of moles of these corresponding substances as weight by molecular weights. Molecular weight of this thing is 108 plus 127, that is 235. Now we all know that in this problem, in this question, we have been given that the weight of the mixture is 1.618 gram, and here I will be obtaining the weight of AgCl. Over here I will be getting the weight of AgI, and when I equate that to 1.618, I will get an equation which is having only one unknown, that is nothing but x. So now we will be solving this for x, and after solving for x, when you are asked to find out the percentage composition of KCl, you will divide this x by total weight with the 100 multiplication will fetch you the percentage composition of the mixture, which is turning out to be 39.6. Therefore, the percentage of Ki will be 100 minus this, that is 60.4%. So these are your answers for this particular question. Here in this problem, we have a 5 ml of 8 normal nitric acid, that is HNO3, 4.8 ml of 5 normal HCl, and a certain volume of 17 molar H2SO4, which are mixed together and made up to 2 liter. From this 30 ml of this solution was exactly neutralized by 42.9 ml of Na2CO3, that is sodium carbonate solution, which is prepared by taking 1 gram of Na2CO3 dot 10H2O in 100 ml of water. Then you are asked to find the weight of sulfate ion in the solution. Now you see in this particular problem, you know that there is a container which is added the HNO3, HCl and H2SO4 in certain amounts, and those amounts are specified to you. As far as HNO3 is concerned, it is 8 normal and 5 milliliter. HCl is 5 normal and 4.8 milliliter, and H2SO4 is 17 molar, that is 17 into 2. 2 is the basicity of this particular acid. 17 when I multiply by this 2, I am getting 34 normal, and let us assume that the volume of this H2SO4 which is being taken, which is unmentioned in the problem, as VML. Now this is the acid mixture that you have taken, and you have dissolved that in water so that you can make it to total 2 liter. I mean to say, this acid mixture is initially present in 2000 milliliter. Yes, 2000 milliliter of the acid mixture is picked only 30 ml, and this was titrated with sodium carbonate. You can see that sodium carbonate, being a moderate base, is going to react with all the strong acid that are present over there. So when I use the law of chemical equivalence, saying that the gram equivalence of acid mixture is equal to the gram equivalents of sodium carbonate in aqueous medium. I will be writing this as equivalents, gram equivalents of nitric acid, gram equivalents of HCl, and gram equivalents of H2SO4 are being equated to the gram equivalents of sodium carbonate. Now, since you are aware of the equivalents of each and every substance that is involved, normality into volume, because normality is equal to gram equivalents by volume in liter. So when you multiply normality with the volume, you will be getting the gram equivalents of a substance. You know that this is 8 normal, and when I multiply this with 5 divided by 1000 is because I have been given the volume in milliliter. I am converting that into liters by dividing it with 1000. So normality into volume will give you the gram equivalents. These are the gram equivalents of HNO3. Then you have the gram equivalents of HCl, and gram equivalents of H2SO4. Now you know that these are the gram equivalents of this acid mixture which is present in 2 liters. Whereas when you did the titration, you took only 30 ml and the pertaining gram equivalents of Na2CO3 are mentioned. You can see 1 gram of Na2CO3 dot 10H2O was taken. So when I divide the weight with the molecular weight, I will be getting the gram moles. When I divide this with the equivalent weight, I will be getting the gram equivalents. So now you see weight, I am going to divide directly with the gram equivalent weight of Na2CO3, that is gram molecular weight divided by its n factor. Just see, now the molecular weight of Na2CO3 dot 10H2O which is being given to you is 106 plus 180, that is 286. When I divide the gram molecular weight with the n factor of sodium carbonate, in this particular case the total charge is being taken as the n factor. So when I divide this with 2, I will be getting the gram equivalents of Na2CO3. But please notice that these are the gram equivalents that are present in 100 ml. So we have to calculate the concerned normality. So when it's given that this 1 gram of Na2CO3 dot 10H2O is present in 100 ml of water. Hence when I take the normality of the solution, I am going to divide the gram equivalents with the volume in liters. Now this solution is taken 42.9 milliliter. Hence now when I am dividing the normality with the volume, I am getting the gram equivalents of Na2CO3, or else these are the gram equivalents that are present in 100 ml. For 42.9 ml, how many equivalents do we have? This is how we are going to obtain this value. As I told you, once again I am repeating, these are the gram equivalent that are present in 100 ml. Then for 42.9 ml, it will be this much. These are the gram equivalents which are being used for the titration. But you see that these are used only for 30 ml, whereas this amount is present per 2 liter. So these are the gram equivalent that are present in 2 liter of the solution. So now use this simple relationship to find the volume of H2SO4 which is being used, which is equal to VML. After finding out the volume, the gram equivalents of H2SO4 is equal to normality into volume in liter. You know that here the normality of H2SO4 is being taken as 34. So when I multiply this with 34 and V by 1000, I will be getting the equivalents of H2SO4. And after getting the equivalents of H2SO4, I know that the number of moles can be obtained by dividing this with the n factor of H2SO4, which is nothing but 2. So this is turning out to be 17 V by 1000. Now these are the gram moles of H2SO4 present. Now you know that 1 mole of H2SO4 contains 1 mole of sulfate. So these are nothing but the number of moles of sulfate ions. So finally the number of moles of sulfate ions here, which is equal to molecular weight by molecular weight, turning out to be 17 into V divided by 1000. So therefore weight of sulfate ion which you have been asked to find out is 96 into 17 V divided by 1000. Here I will be substituting the value of V directly to obtain the weight of sulfate ions, which is being calculated as 6.528 grams. After this simplification, you will be getting the weight of H2SO4 as 6.528 5 to 8 grams as your final answer. We have 0.5 gram mixture of potassium dichromate and potassium permanganate was treated with excess of potassium iodide in acidic medium. Iodine liberated required 100 milliliter of 0.15 normal sodium thiosulfate solution for complete neutralization. Then you have been asked to find the percentage composition of the mixture. In this problem we have once again the mixture of two substances. This time both are very strong oxidizing agents. We know that potassium dichromate and potassium permanganate are very strong oxidizing agents, and their aqueous solutions are being added potassium iodide, where the products under acidic conditions. See my dear students, here if you are comfortable with the chemical reaction that are taking place over there, you can write the complete reaction and balance accordingly to solve this problem. Whereas if you are not sure about the products that are obtained, or you are not sure about the balancing of this complex reaction, then it is always advised to avoid mole concepts where you may require the balanced equation. The advantage of equivalent concept is that you might not require the balanced chemical equation. So in this case, since we are not sure of the acid that has been used, I would like to simplify this by just writing the products without balancing it. I am going to use the gram equivalent concept. I am going to say, you know that under acidic conditions chromium changes its oxidation state into +3 and manganese goes to +2 because they are oxidizing agent, they are going to get reduced, and reducing agent is going to get oxidized. So this is the reducing agent here, whereas these two are the oxidizing agent. So here you can see that both oxidizing agents are collectively reducing potassium iodide, which is a very strong reducing agent. Now as per law of chemical equivalence, you say that the gram equivalence of K2Cr2O7 and the gram equivalence of KMnO4 under acidic conditions is equal to gram equivalence of potassium iodide, because gram equivalence of acid equal to base or oxidizing agent equal to reducing agent, which is equal to the gram equivalence of I2, because you can see in either cases the entire potassium iodide had been converted into iodine. Now this iodine, which is obtained in both the reactions, collectively had been neutralized by sodium thiosulfate, and the information provided to you is regarding only sodium thiosulfate, which is 0.15 normal and 100 milliliters. And you know that since these two are reacting, again the gram equivalence has to be equated. Now what I will do is I will assume, since I had been given the total weight of the mixture as 0.5 gram, I will assume this as x gram and this will be 0.5 minus x gram. Now when I am using the equivalent concept, what I will be doing this time is, since there is no volume normality which is being mentioned for this, but the weight terms are given, I will write the gram equivalence in this case as weight divided by equivalent weight, that is molecular weight of K2Cr2O7, that is 2 into 39 is the atomic weight of potassium, plus 2 into 52 is the atomic weight of chromium, plus 7 into 16, whatever it turns out to be. When I divide the molecular weight with the n factor of potassium dichromate, you can see my dear students, n factor of potassium dichromate in this reaction. We know that n factor is defined as the total moles of electrons involved in the particular redox reaction per mole of the substance. Here you know that chromium is changing its oxidation state from +6 to +3. One chromium to change from +6 to +3, it requires 3 moles of electrons. There are 2 chromiums, hence n factor is 6. I am repeating, one chromium to change from +6 to +3, it requires 3 moles of electrons. There are 2 chromiums which are changing the oxidation states, n factor is 6. And you know that manganese is changing its oxidation state from +7 to +2, and n factor is turning out to be 5 as well. The change in oxidation state in this case is 5. So when I am dividing the molecular weight with the n factor of potassium dichromate, I will be getting the gram equivalent. Weight divided by equivalent weight plus weight of this 0.5 minus 6 divided by equivalent weight of this compound 39 plus 55 plus 64, the total molecular weight of this compound. Molecular weight divided by the n factor will give you the equivalent weight. Weight by equivalent weight will give you the gram equivalence. in case of gravimetric calculations. But at that side you had been given information regarding normality and volume. You can use to find the gram equivalents, normality into volume in liter. So 100 milliliter, that is 0.1 liter. So now by solving this expression, you can find the value of x again, and you will be saying that the weight percentage of K2Cr2O7 in the mixture is weight of K2Cr2O7 by total weight multiplied by 100. This is turning out to be 14.6%. Hence the weight percentage of KMnO4 is 100 minus all this, that is 84 point. So this is the answer for this given question. We have 0.05 gram of a commercial sample of potassium chlorate containing some KCl. On decomposition, liberated just sufficient oxygen for the complete oxidation of 20 milliliter of carbon monoxide. The volume of CO was measured at 27 degrees Celsius and 750 millimeter of the mercury pressure. So you have been asked to calculate the percentage purity of the sample of KCl03. In this problem, you have to understand that the KCl03, which is a solid, had been taken to heat to obtain the KCl and O2. I am balancing this equation simultaneously. And you see, whatever oxygen which is liberated in this particular reaction had been used for a certain purpose. This had been used to completely convert this carbon monoxide into the carbon dioxide gas. So you have been asked on this basis to find the percentage purity of potassium chlorate, that is weight of pure potassium chlorate by the total weight of the commercial sample into 100. So to get the weight of pure potassium chlorate, I might have to link the substance which is present in both the reaction, which is nothing but oxygen. And to link up the oxygen, we need to get the information about the CO which has been provided to you. And as we know that for an ideal gas n mole, we write the number of moles as PV upon RT to find the number of moles of this particular gas. In this case, the pressure had been mentioned as 750 mm of pressure, and volume is given as 20 milliliter by R value in liter atmosphere is 0.0821, and temperature is specified as 300 Kelvin, that is 27 degrees Celsius. These are the number of moles of carbon monoxide what we have with us. From this information, we will be finding out the oxygen moles, because we have to get ultimately the moles of oxygen, which is a common substance between these two reactions. So to get the number of moles of oxygen, you know that the mole ratio of these two substances is 1:half. That means if I get this many moles of carbon monoxide, I will be getting the number of moles of O2 as half of the entire thing. Half of the entire thing. You can see 1:1/2 is the mole ratio. Then for this many moles, I can expect half of this entire thing to be obtained. I mean to say 1/2 times of these are number of moles of oxygen which are obtained. Now, before I simplify this, I will assume this whole value as x. I will assume this entire value as x. You calculate and get the value of x. I am assuming it presently as x. Now you know that the ratio, because you have been asked information regarding KCl03, you have to get the link between these two by mapping their stoichiometric coefficients. You know that if it is 3/2:1, I can call also it as 1:2/3. For every 1 mole of O2, 2/3 moles of KCl03 is involved. 3/2:1 or 1:2/3. For every 1 mole of O2, 2/3 moles of KCl03 is involved. For every x mole of O2, I can expect the number of moles of KCl03 which is undergoing the change, that is pure substance, is 2/3 times of x, which is nothing but weight of KCl03 by molecular weight of KCl03, that is 39, 35.5 and 48. So therefore, finally, I will be finding out weight of KCl03 pure by cross multiplication, 2/3 times of 39 plus 35.5 plus 48. This is the gram molecular weight of KCl03, and I am writing here the value of x intact. So now this is the weight of pure K03 and the percentage purity of the sample is equal to weight of K03 pure by total weight of the sample is given as 0.05 gram into 100. That means hold this value, we substitute here to get the answer as 65.4%. That means this sample, commercial sample, has only 65.4% purity of K03. We have a solution which contains 4 gram of mixture of sodium carbonate and sodium chloride in 250 ml, and 25 ml of this solution required 50 milliliter of 0.1 normal HCl for the complete neutralization. Hence you had been asked again to find the percentage composition of each in the sample. And you know that since you had been given NaCl and Na2CO3, of these two, you know that only Na2CO3 is going to react with HCl. Now you know that this is a simple reaction which is taking place because we all are aware of the fact that the salt of a strong base and strong acid neither react with strong acid nor react with a strong base. I am repeating, the salt of strong base NaOH and strong acid HCl. The salt of strong base and strong acid neither react with strong acid nor react with strong base itself. So I can't expect this NaCl to react with HCl, whereas HCl being an acid, strong acid, will react with a alkali, that is sodium carbonate, because of the presence of carbonate and this is alkaline in nature, this will undergo hydrolysis in water. So when I carry out the reaction between these two, any carbonate when dissolved in mineral acid, as we have seen, is going to evolve CO2 gas. Now when I simplify or balance this equation, I can use this as a simple volumetric equation, hence I can balance this equation to use the mole concept also. Now let's apply both the concepts and you understand the difference, which one is better one. Now when I want to apply the mole concept, I should have first of all the balanced chemical equation, which indeed I have. So I am using here the mole concept to solve the problem. Now I had been given the number of moles of HCl. You can see, my dear students, that the normality is given as 0.1, which is also equivalent to the molarity of HCl, because n factor of HCl is equal to 1. There are only one replaceable hydrogen atom present per mole of HCl. Per mole of HCl, the number of moles of H plus replaceable is known as the n factor of HCl, which is nothing but the 1. Now when I divide the gram equivalents with n factor, I am going to get gram moles. When I divide the normality with n factor, I am going to get the molarity. Since the normality is given as 0.1 by n factor, it is going to give you molarity, and when I multiply the molarity of the solution with its volume in liter, I am going to get the gram moles of HCl, that is 50 into 10 to the power minus 4 are the gram moles of HCl. Now for every 2 moles of this HCl, you can see 1 mole of Na2CO3 is only reacting, hence the number of moles of Na2CO3 which have reacted over here are half. 2:1 is the mole ratio. Half of the above value is 25 into 10 to the power minus 4, that is 50 by 2 into 10 to the power minus 4. Now these are number of moles of Na2CO3 which has to be written as weight upon molecular weight. So weight of this thing is equal to this many grams. So you can find this way. Or when you are using the equivalent concept, irrespective of the stoichiometric coefficient, you will write the gram equivalents of two substances reacting are always equal. Gram equivalents of HCl is normality into volume in liter. You can see normality is 0.1 into volume in liter, which is turning out to be same, that is 50 into 10 to the power minus 4. These are the gram equivalents of HCl, which is equal to weight of Na2CO3. I am writing the gram equivalents of Na2CO3 as weight of Na2CO3 divided by equivalent weight, gram equivalent weight. I am going to get the gram equivalents by dividing the weight with the gram equivalent weight, that is molecular weight by n factor of Na2CO3. As I just told you, it has to be regarded as the total charge in this case. It is 2 into plus 1. Now you are going to get this weight of Na2CO3 as the same as I got in that particular case. Now whether you proceed by mole concept or equivalent concept, the answer is going to be same, which is nothing but weight of Na2CO3 divided by the initial weight of the mixture, is 4 gram into 100, which is turning out to be 66.25%. Then 100 minus of this will fetch you the value of NaCl. Here NaCl is just playing the role of a additional substance. It has got nothing to do with the entire reaction. You can see here the product is also NaCl, but we are not using NaCl at all because the information is provided to you regarding the HCl. You have to find out the information about Na2CO3. You can proceed either by mole concept or equivalent concept to get the answer. It's up to you, your convenience.